The interior of these stones cannot be machined by any drill bit that exists today. Not in 1970. Not in 2010. Not now. And yet someone made them, centuries before the first metal tool was found anywhere on this continent. In 2023, a team of engineers ran high-resolution 3D laser scans across the H-blocks of Puma Punku, a site in the Bolivian highlands that has quietly baffled archaeologists for over 100 years. What the scans returned wasn't just data about surface carvings. They captured the interior geometry of the joints. And the people reviewing those renders went quiet. Because the tolerances were wrong. Not impressive for ancient people, wrong. Wrong in the way that defies the manufacturing logic of the era entirely. We're talking about internal angles that converge with sub-millimeter precision in cavities that no hand tool can enter. Recesses cut into stone at compound angles that, when assembled, interlock in 3 dimensions simultaneously. Here's what nobody is telling you in the mainstream coverage of this scan. The outside of these blocks isn't the mystery. The outside has been studied for decades. The mystery is what the scans revealed inside, the geometry hidden within the joins. The part that was never meant to be seen. The part that, according to every manufacturing process we've ever attributed to this site, should not be there. This is that story. And it gets significantly stranger. Puma Punku sits at 3,840 meters above sea level, on the Bolivian Altiplano near Lake Titicaca. It's part of a larger complex called Tiwanaku, a civilization that predated the Inca by roughly 1,000 years. Most historians date Puma Punku's construction somewhere between 500 and 800 AD. Some push it earlier. The official story is a sophisticated but ultimately human construction project, built by a highly organized labor force using stone-cutting techniques refined over generations. That story has held, more or less, for a long time. But the scans didn't just add detail to that picture. They introduced geometry that the story cannot currently explain. First, you need to understand what an H-block actually is. These are not decorative stones. They're not grave markers or ceremonial objects. They're precision-engineered structural components, modular building blocks, H-shaped in cross-section, designed to interlock with each other and with other block types in a specific, repeatable configuration. They weigh between 100 and 130 metric tons each. The stone itself is diorite and red sandstone, among the hardest materials available in the ancient world. For decades, the external features of these blocks have been documented obsessively. Straight channels. Right-angle cuts. Symmetrical recesses. Multiple researchers noted the cuts appeared machine-precise, edges sharp to within fractions of a millimeter, surfaces flat in ways that exceed what chisels and abrasives produce in hard stone. The standard explanation invoked patient, skilled labor. Thousands of hours. Stone-on-stone grinding. The gradual perfection of form. It was a reasonable theory. Until the interior geometry was mapped. The 3D scans were conducted as part of a broader archaeological documentation project. The technology used, structured light scanning combined with photogrammetric overlay, is the same kind of system used to reverse engineer aerospace components and forensic crime scenes. It doesn't interpret. It measures. And it produces renders that show you geometry with an accuracy of less than a millimeter across the full surface of a structure. When engineers applied this to the H-block joints, they were expecting to confirm what was already assumed, that the blocks fit together tightly, impressively, with a kind of craft that ancient civilizations are increasingly being credited for. What they found instead were internal recesses with compound angle geometry. Specifically, cavities inside the joint interfaces that are not visible from the exterior of the assembled block. Cavities that, when two blocks are joined, become entirely enclosed. Inaccessible. Hidden inside the stone. And those cavities are machined. That word deserves weight. Machined. Not carved. Not abraded. Machined, meaning the angles are consistent across the internal face in ways that require controlled, repeatable cutting action. Not the variable pressure of a hand tool. Not the unpredictable grain response of stone on stone. The interior geometry shows tooling consistency that implies a process. A controlled, repeatable, precise process. Applied to the inside of a joint that, once assembled, no tool can ever enter again. And that is where the official explanation starts failing in ways it hasn't failed before. Here's the problem that the scans made impossible to ignore. If you're cutting stone with hand tools, with chisels, stone picks, abrasive powders, and the grinding patience of skilled labor, your tooling marks tell a story. They're directional. They vary in depth. They follow the path of the hand. They respond to the grain of the stone differently in different locations. They are, in a technical sense, human. And they're visible. The record of how the cut was made is preserved in the cut itself. The interior joint surfaces of the H-blocks don't show that record. The scans show surfaces with angular consistency that runs counter to hand tooling physics. The recesses maintain the same depth across their full interior extent. The compound angles, the places where 2 or 3 planes meet inside the cavity, converge at values that are geometrically precise to a degree that has no precedent in any other known ancient stonework. And here is the detail that the researchers reviewing the scan data found most disturbing: the interior corners. In standard stone carving, interior corners are among the most difficult features to produce cleanly. The tool has to change direction. The access becomes constrained. The cut quality degrades. This is true even with modern hand tools. In hard stone, interior corners left by hand cutting show radius, rounding, imprecision. The geometry softens where the hand loses leverage. The H-block interior corners don't soften. They are crisp, consistent. The angular junction between 2 intersecting planes inside a hidden cavity is as precise as the exterior face of the block. That is not what hand tools produce. That has never been what hand tools produce. But this wasn't the disturbing part. Because the geometry alone, as strange as it is, could theoretically be attributed to some advanced technique we haven't recovered. Some tool we haven't found. Some method we haven't reconstructed. The disturbing part is what the geometry implies about sequence. To understand this, you need to think about manufacturing logic. If you're building a joint, any joint, in any material, the sequence of operations matters. You cut the external form first. Then you cut the mating surfaces. Then, if the joint requires interior geometry, you cut that last, while the material is still accessible, before the joint is closed. That's basic manufacturing logic. It's true in woodworking, metalworking, stoneworking. You don't cut the inside of a closed joint because you can't. The inside is only accessible when the joint is open. The interior geometry of the H-block joints is consistent with a joint that was cut while closed. Or, and this is the interpretation the scan data forces you to consider, a joint that was formed rather than cut. Formed. Not carved into existence piece by piece. Formed in a single operation that produced the exterior and interior geometry simultaneously. That word, formed, points in directions that mainstream archaeology is not currently equipped to follow. Because there are only 2 manufacturing processes that produce interior joint geometry without interior tool access. The first is casting, pouring liquid material into a mold that shapes both exterior and interior simultaneously, then allowing it to solidify. The second is a form of precision machining where the cut is made across the full cross-section of the material before assembly. Essentially, you're not cutting a joint, you're cutting 2 mating surfaces in a single pass. Neither of these is the hand-carving narrative. Now, before we follow that thread, there's a piece of physical evidence that the 3D scan data made newly relevant. Evidence that researchers have been sitting on for decades. Evidence that, in light of the interior geometry, looks considerably less speculative than it once did. In the 1970s, a geological analysis of samples from Puma Punku blocks, conducted outside the official archaeological framework, returned results that initially seemed like contamination error. The stone matrix in several samples showed a distribution pattern inconsistent with naturally quarried diorite. Specifically, the aggregate composition suggested a material that had been mixed at some point in its history. particles distributed through the matrix in a way that doesn't occur naturally in a single geological deposit. This finding was shelved. It didn't fit the model. The samples were small. The methodology was disputed. The 3D scans didn't directly address this, but they made it relevant again. Because if the blocks were not carved from quarried stone, if they were instead cast from a geopolymer or hydraulic limestone compound, then the interior joint geometry becomes explicable. A cast block, formed in a mold with interior geometry built into the mold itself, would produce exactly the scan results we're now looking at. Crisp interior corners. Consistent depth. Compound angles that converge precisely. No tool marks because there were no tools, there was a mold. This is not a fringe theory. Geopolymer concrete, the idea that ancient builders may have used a form of rock casting rather than rock cutting, has been seriously proposed by material scientists, most notably by Joseph Davidovits, whose analysis of Egyptian pyramid blocks suggested similar casting chemistry. The Bolivian highlands have the raw materials. Volcanic ash. Alkaline lake water from Titicaca. Aluminum silicate compounds in the local geology. A geopolymer process is chemically viable here. And if it's true, the implications extend far beyond Puma Punku. Because here's what that means for the official timeline. If these blocks were cast, if the construction technology was not advanced stone carving but advanced materials chemistry, then everything we've concluded about the civilization's capability level needs recalibration. We've been measuring them against a tool-making benchmark. We should have been measuring them against a chemistry benchmark. And by that measure, they weren't primitive. They were operating in a completely different technical paradigm. One that we lost. There is a third element of the scan data that has received almost no mainstream coverage. And it is arguably the most structurally significant. The H-blocks are designed to be modular. This is well established. But the scan data revealed something about the modularity that wasn't previously understood, the tolerance stack. In precision manufacturing, when you assemble multiple components that each have small dimensional variations, those variations add up. This is called tolerance stack. It's one of the central challenges in any modular manufacturing system. You have to engineer each individual component to such tight tolerances that the accumulated error across multiple components remains within acceptable bounds. The H-blocks show tolerance stack control consistent with a designed manufacturing system, not a craft tradition. Specifically, when the scan data from multiple H-blocks at Puma Punku is compared, the dimensional variation between individual blocks is statistically smaller than what would be expected from any hand production process. The blocks aren't similar. They're not close. They're interchangeable in the way that machined parts are interchangeable, because their variation falls within a range that appears to have been controlled. That is a manufacturing concept, not a craft concept. Interchangeability as a design principle. The idea that any block of a given type can mate with any other block of that type without fitting adjustment is, in the Western industrial tradition, a relatively modern innovation. It's associated with the development of machine tools in the late 18th century. The precision required to produce truly interchangeable parts consistently was considered a major technological achievement of the industrial era. The H-blocks appear to demonstrate it. 1200 years earlier. In the Andes, in one of the hardest stones on Earth. And we still don't know who built them. Here's what the 3D scan data has actually done. It hasn't proved an exotic origin. It hasn't established anything that mainstream archaeology is prepared to officially accept. What it's done is much more precise, and in some ways much more troubling. It has closed off certain explanations. The skilled hand labor model cannot currently account for the interior joint geometry. The stone-on-stone abrasion model cannot produce the tolerances the scans measured. The trial and error craft refinement model cannot explain the interchangeability distribution. Every conventional answer to, how did they build this, runs into the scan data and stops. That's a specific kind of scientific problem. Not an unsolved mystery, where we simply haven't found the answer yet. A constrained mystery, where the data is actively eliminating candidate answers faster than new ones are being proposed. And the answers being eliminated are the foundational assumptions of the existing archaeological model. The site was always strange. Now it's precisely strange. And precision changes everything, because precision means the strangeness isn't ambiguous. It's measurable. It's repeatable. It will be there in the next scan, and the scan after that. Whatever built the H-blocks of Puma Punku understood something about material forming, tolerance control, and joint geometry that we are still trying to reconstruct. And they built it at 3,800 meters above sea level, far from any known industrial base, in a civilization that, by our current model, should not have had the manufacturing paradigm to produce it. The scans are public. The data is accessible. The engineers who reviewed the renders made their notes available, quietly, through technical forums rather than press releases, because the implications were not the kind that career archaeologists are positioned to explore without risk. But the geometry doesn't care about careers. It doesn't care about the model. It doesn't soften its interior corners to make the explanation easier. The blocks are still there. The joint surfaces are still precisely what the scans say they are. And the civilization that made them, whatever they actually were, whatever they actually knew, is still not fully understood. What we do know, now, with laser scan certainty, is this. They were not doing what we thought they were doing. And whatever they were doing, we haven't figured out how to do it yet. That should bother you more than it does. Because Puma Punku isn't the only site where the physical evidence outpaces the official explanation. It's just the one where someone finally brought precise enough instruments to make the gap impossible to dismiss. The question isn't whether the H-blocks are anomalous. The question is what else we've been measuring with the wrong benchmark.